Good afternoon, and thank you everyone for joining us. We are honored to have Tim Theiss. Am I saying that correctly, Tim?
It's actually Theiss.
Theiss, it is Theiss. Okay. Apologies. We are lucky and honored to have Tim Theiss from the Oak Ridge National Laboratories with their Bioenergy Technologies program. Mr. Theiss has been on the staff at ORNL since the late 1980s, starting as a research development staff and moving all the way up as now a program manager. Since 2011, he has managed the program manager for the DOE Efficiency and Renewable Energies Bioenergy Technologies program, which the program itself includes research on feed supply and logistics, biomass conversion technologies, and strategic analysis of sustainability of bioenergy. His specific areas of interest include additive manufacturing with bio-derived materials, low carbon fuels for maritime applications, bioenergy for carbon capture and sequestration. In 2017, he was named the leader of the Renewable Energies Group for the Environmental Sciences Division and was recently named the interim section head for biodiversity and sustainable systems section in ESD. He comes to us from Tennessee Tech, where he got his bachelor's in engineering and a master's from Virginia Tech in engineering mechanics. Before I read the rest of his CV, I think I'll stop there and I'll let Tim start off with our presentation. Tim, it's all yours. Please start. Okay. Sorry, real quick, before I forget, if anyone does have any questions or any comments, please feel free to add those in either the Q&A or chat function, which is located at the bottom of your toolbar within Zoom. You'll also be able, as Tim is sectioning off parts of his presentation, he'll be taking questions and answers at the end of each section. With that, Tim, please go ahead.
Okay, well, thank you very much. I appreciate the introduction and I appreciate the opportunity to speak to you today. This is a very timely and germane topic looking at the intersection of the ag and the energy sectors. And so I'm delighted to be a part. Looking forward to a discussion on the use of biomass to replace transportation fuels. And so just as an overview of what we will be covering today, start off with a little bit of motivation and background on transportation energy use. There's just some things that we kind of need to have a common understanding about. So we'll walk through some of those. Talk about biomass availability, how much there is, where it is, what the different conditions are. We'll spend a fair amount of our time talking about the aviation sector and decarbonization of that sector. We'll explain why that's important and what's unique about that. We'll talk about the maritime sector and the decarbonization in that sector as well. And then, although there's going to be quite a few trends and needs throughout the presentation, I've got a few specifics that I've called out toward the end, and then hopefully some questions and answers along the way. As far as motivation for this, there's actually quite a few different ways that we can approach this and look at it. Global climate change is one of the most significant motivating factors for this. And so I've shown a chart that shows the change in the global temperature over the last century or so. And you see the variation, you see the significant rise in the temperature that's occurred since about the 1970s or so. But there's a lot of variability there. And so we always are asking our question, how did this come about? What's causing this? And so we can model some of this and we can compare the models that look at natural factors alone and compare that with what we've actually observed. And we see that that's part of it and is consistent up until about the 60s or the 70s, but it doesn't explain the rise in temperature that's occurred over the past few decades. When we add natural and human factors to that, we find that the model does match the observed data. And so we are drawn to the conclusion that the climate is warming, that's beyond doubt, and that human factors are contributing, at least in a significant way, to this temperature increase. And so as a background for this global issue, basically the scientific data is compelling. There is a rise in greenhouse gas emissions, or GHG levels, primarily CO2, and that's bringing about an increase in global temperatures. There's also a very compelling need to reduce the CO2 levels in all sectors of the economy and across all countries. And so we'll talk about that just a little bit more. The use of renewable energy has come on strong over the past few decades, and it is a way to replace fossil fuels, which we're largely still dependent on, in a process called decarbonization. And so we're basically substituting the fossil fuel, the carbon in fossil fuel, with renewable energy. That can also lead to and promote energy security. Just as a reference, Ukraine is very interested in the increase in renewable energy, and part of the reason basically is energy security associated with oil and gas, primarily from Russia. Complete decarbonization is considered to be impractical or impossible, but the goal is to reduce as much of the CO2 emissions as possible and then sequester or store the remaining CO2. Renewable energy, particularly wind and solar, have really grown dramatically over the past 15 or so years. This trend will need to continue in order to meet the carbon-free electricity goals that we have in place by 2035, and it needs to continue beyond that as a driver for decarbonization in other sectors. We'll talk about that as well. In 2050, that's the target for the primary decarbonization goals. That's what we have and where we're trying to realize these goals and objectives. It seems like that's a long way away, but in fact, with some of these technologies and the way that it takes, the time that it takes to implement these, that's not very long at all. And then I strongly believe that the U.S. has a leadership role in this, not just because we're the world's leading economy and the world's largest economy, but because we're innovators and we don't want to be left behind technically. There are ways that we can help influence the decarbonization strategies of the future, and we want and need to be a part of that process for the duration. Transportation. Transportation sector is now the largest contributor to CO2 emissions. It is considered the most difficult to decarbonize. It is almost completely reliant on petroleum at this time. We'll talk about the exceptions and the role of biofuel in just a few minutes, but it's primarily a petroleum-based sector. It will continue to be the largest contributor to our global, to the U.S. CO2 emissions for some time. And you can see in the chart on the right, the transportation sector is shown in blue. Basically, the part over here on the left is real data, and then we've got projections that are looking out into the future. You can see the commercial sector, the residential sector, the industrial sector, the power sector, and the transportation sector all contributing, but transportation is the largest. Also notice that the electrical power sector has decarbonized to a significant level. The carbon intensity has dropped quite significantly, due in large part to the advent and use of wind and solar for power generation, also due to fuel switching. The electrical sector has switched primarily from coal to a significant amount of natural gas. And so that reduced carbon intensity with natural gas has also led to this decline in the carbon intensity of the electrical power sector. Current projections, however, do not show continued decreases in the electrical power sector or in fact in any of them. And so that means that we're going to need to realize new solutions if we're going to reduce the CO2 emissions that is part of our economy at this point in time. Another way of looking at it, again, we're looking at the transportation sector, and then amongst the other sectors, that's the pie chart on the left. It is the largest source of GHG emissions. There are different modes that lead into this transportation sector overall, and they require different fuels. I would direct your attention to the upper right-hand part of the pie chart, passenger cars and trucks, which make up largely 50% of the GHG emissions of the transportation sector. And those generally are considered to be replaceable with EVs and batteries. And so EV sales have grown rapidly recently, and they will be able to replace a significant portion of cars and trucks, passenger cars and trucks. It will take some time, but that's considered a relatively straightforward substitution. And so these sectors, passenger cars and light trucks, basically have a clear pathway for decarbonization. It's when we get to the others that are shown here in the lower right-hand portion of this pie chart. Heavy-duty vehicles, buses, 18-wheelers, off-road transportation, ag equipment, construction equipment, mining equipment, so on and so forth, rail, water or marine applications in aviation. These are considered the more difficult to decarbonize subsectors of the transportation infrastructure, and they're going to have quite a bit of difficulty using batteries. Batteries simply do not have the same energy capacity or energy storage as do liquid fuels. It's still about an order of magnitude difference in those. And so that's expected to be a trend that continues for some time. Biofuels are a viable replacement, but biofuels are used now. We'll talk about that here in just a second, but they cannot replace all of the transportation fuels. Biofuels and the biomass that goes to derive these fuels are a limited quantity, and we'll talk about that in time. A little bit of background on petroleum refining and the fuel consumption associated with the transportation sector. I think we're all aware that crude oil is refined. It's largely a distillation process, and different components or fuels come out based on different temperatures. They have different weights or cuts and basically are used to supply essentially all of our transportation needs and also our industrial needs. And so the naphtha that you see at the top is largely used as a feedstock for plastics and things of that nature. And then you see the lighter cuts, gasoline, kerosene, and then the heavier cuts, the distillates, diesel oil, and then the real heavy cuts, the heavy fuel oil, and the residual asphalt. And so that's basically how petroleum refineries work, is they're mixing and balancing all of these and sell all of them. And that's how they're able to make the large amounts of money that they do. The petroleum products that come out of a barrel of crude oil are in the chart on the right. And we can see that out of a barrel, a 42-gallon barrel of crude, we have about 20 gallons. Did I say that right? A 42-gallon a barrel of crude is 42 gallons, of which 20 gallons is gasoline, about 12 and a half is distillate or diesel fuel, 3.5 gallons is jet fuel, and then the other is 6.3 gallons. That equates to about 300 billion gallons a year. And you can see that gasoline is about 136 billion gallons, diesel fuels 85 billion gallons a year, jet fuel roughly 24. Crude oil consumption in 2021 is just a little bit less than 20 million barrels of crude a day. That equates to 230 barrels per second, or roughly 10,000 gallons of some kind of petroleum product used every second in this country. So it's a staggering amount, and it's going to take a monumental effort to decarbonize this sector. So decarbonizing the transportation sector is going to require multiple solutions, and liquid fuels of some form are going to be required, particularly for the aviation and marine sector, for the foreseeable future. Battery electric vehicles appear to be fine and viable for most typical passenger vehicles. The duty cycles match up well with what batteries can handle. Fuel cell electric vehicles may be able to provide power for the medium duty vehicles. And so you see on the chart on the right where VW is comparing the weight of the different vehicles and their mileage per day. And so light duty vehicles are here in the lower left, and then medium duty vehicles are in the center. Thought that fuel cells could provide an option here, but basically it's pretty well accepted and understood that these difficult to decarbonize sector, marine, aviation, and rail, and maybe also long-haul trucking, are going to require the added energy density associated with liquid fuels for the foreseeable future. Also, it's important to note that these larger vehicles, planes and ships and so on, have a much longer fleet turnover rate. So the light duty fleet turns over about every decade or two, and it's significantly longer than that for these maritime, large ocean-going vessels and for planes. They can stay into service for several decades, in fact. And so that tends to promote the use of liquid fuels and their continued reliance. So looking at biomass availability, Basically, with the Department of Energy, we've done some significant studies in this area, and most of us recognize that biofuel is a little bit different in that plants, grasses and trees and everything else take CO2 out of the atmosphere, combined with energy from the sun, convert that into biomass. That adds soil or organic carbon to the soil, and it also can be used when that biomass is harvested. It can be used to make biofuel, bioproducts, or even power to the grid. We can, in some of these processes, capture that CO2 and then return it and sequester it. So biofuel, straight by itself, is a low carbon alternative, not quite decarbonized, but if we sequester the CO2 that comes off of the process, we sequester it and store it, then that can have a net negative effect. And so we do life cycle analysis looking at the entire process to come up with these types of calculations and these types of metrics, if you will. Biomass resources that we currently use. On the left, you'll see corn. That's used primarily. Starch is used for ethanol production today. The protein is generally extracted and used for animal feed, and so that part is not lost. That's used to make roughly 15 billion gallons a year of ethanol. And then we also use soybean, canola, and corn oil, along with cooking oils and animal fats, commonly referred to as fats, oils, and greases. We use them to produce roughly 2.5 billion gallons of biodiesel and then renewable diesel. So we have ethanol is used primarily in the light duty fleet. I think all of us are used to that little sticker on the gas pump that says may contain up to 10% ethanol. And then diesel, biodiesel, most of us have probably heard of that. The amount that is used, the quantities are such that it is intended and it's deliberately set up not to disrupt food production or cause undue spikes in the cost of food. And so basically it is a food and fuel process that's being implemented. This is roughly 18 billion gallons total out of roughly 300 billion gallons of that's used for fuel. So it's a significant amount. 15 billion gallons is quite a bit, but it is not a majority share by any stretch. It's still a relatively small amount in the transportation sector. Biomass resources that are also available today are listed here. They're readily available and generally considered to be fairly abundant. The composition is variable, and that's understandable when we understand what they are. They're ag residues, largely corn stover, the stalk that's left over. They're forest residues, so forest thinnings, the small parts of trees that are not used when the tree is harvested for pulpwood, and it's waste-based biomass. Municipal solid waste is considered to be biomass and renewable in that respect. They can be relatively inexpensive. With waste-based fuels, MSW for example, municipal solid waste, you can get a tipping fee or be paid to take it away. However, it's not always easy to collect, and it is highly variable, and frankly it's dirty. It's waste. It comes into the processing facility with a significant amount of moisture, dirt, rocks, and everything else. So it's hard to process, but it is a resource that's available in significant quantities. In the future, we believe that there will be other biomass that's available, primarily energy crops. These are crops that are grown specifically as a feedstock for conversion into the fuels or products. And so we see that there are herbaceous feedstocks. Switchgrass is shown in the pictures on the top, and then woody feedstocks. Willow is shown in the pictures on the lower left. They are grown simply for their energy value. There's multiple varieties that can be grown over a variety of different regions. And so you would want to have regional specific feedstocks. They can be, and generally are, of a higher quality, but they are also more expensive. They do provide the additional environmental benefits such as decreased soil erosion or mitigating soil erosion, improving the water quality, and greater biodiversity. And they're often grown on underutilized land. There's also a significant amount of interest in algae, which does not take a significant amount of land, as a suitable feedstock. And so all of these are in play and are being considered. And so we in Oak Ridge have conducted a series of biomass resource assessment reports. We call them the billion-ton studies. That's going to be apparent here in just a bit. And we've conducted 3 of these, 2005, 2011, and 2016. We're currently working on our 4th iteration of this. And so we go to answer, and we seek to answer the primary question: is there sufficient supply to make a meaningful impact to replace the nation's petroleum consumption? What is the cost of this biomass? Where is it? And then more recently, we focused our attention on what's the overall and long-term sustainability of these feedstocks. We've modeled 44 or more feedstocks with state-of-the-art crop yields. We've developed forest models to look at how much forest resources are available, again, and where, and how much it costs to deliver that. And again, we are working with a variety of other institutions shown in the far right, and we're working to make sure that we protect the long-term sustainability of these resources. We develop a series of maps, such as what's shown here, that shows basically the availability of the biomass at a county-wide level. And so you see a heat or a density map. It is kind of what you would expect. The biomass is available in the Corn Belt and in the plains portion of the country. The portion in blue is the part that's most suitable and productive for biomass. Significant amount of biomass availability along the Mississippi River Valley, Memphis, and north and south. And so all of these projections include multiple sustainability criteria, including forest residue removal limits, ag residue removal limits. You want to leave some of that residue on the crop and forest floor so that you don't make the ag portion of it or ruin the soil productivity. Also, we look at biodiversity protections and the like. And so these heat maps or density maps are made up of a variety of different feedstocks across different regions of the country. And the point here is that a significant portion of the country has the opportunity to contribute to a bioeconomy, but the feedstocks from different regions are going to be very different. What we see in the Southeast is very different than what we see in the Plains, the Northeast, or the Intermountain West. And so it's understanding the relationship between these feedstocks, their overall availability, and basically having a national priority, but looking at different regional contributions. So when we add all of this up, we have the currently used biomass that you can see in the bottom, annual projections that go out to about 2040 or so, although this is a little bit dated. We have the waste-based feedstocks that are also available in the near term, forest resources, ag resources that we show here, and then energy crops that are coming in and growing significantly over time. Those are projected to begin in 2019, so we're a little bit behind on those projections. There is not a national demand for these, so we're not seeing them in large quantities. The overall point of this is, after we meet the demand for food, fiber, and food, the U.S. has ample land and ample capacity to sustainably supply 1 billion tons of renewable feedstock on an annual basis, given adequate market conditions. We believe that the market is more of a determining factor than constraints with sustainability. We have ample protections built into these analyses, and we have it basically relies more on the opportunities and the demand that comes from needing that much biomass for different products. If there's any questions, I can stop at this point and take them. I don't see any. I don't have access to the chat. Okay.
Hi, Tim. It looks like there are no questions yet. I'm sure there will be a few,
Okay.
quite a handful here as we go on, so please continue.
Okay, I want to spend a few minutes talking about sustainable aviation fuel and the decarbonization needs in the aviation sector. And so let's launch into that. As we discussed the petroleum refining a few minutes ago, this is a little bit and a sketch of some of the different methods that are used to convert biomass into biofuels. There's a variety of different biomass feedstocks that are shown on the left, and they are more amenable to different ones of these processes, and these processes make different fuels. Overall, the more that we mess with it, the more that we have to process it and have to deal with it, the more expensive it becomes. That's kind of what we're seeing in the chart across the right. And overall, today, we can produce about 50 gallons of advanced biofuel per ton of biomass. With improved technology, and the current projection is that we should be able to increase that yield to roughly 60 gallons a ton. So that means that out of our billion tons of biomass that's considered to be widely available or ultimately available, we should have about 50 to 60 billion gallons of biofuel. And so how do we want to use it? Again, this is somewhat of a busy chart. It is a chart that the Department of Energy is using increasingly, and I'll direct your attention to the bar chart in the right, and this is showing the future projections of the transportation sector. And you see that it's amplified here in the box on the right. And so with 1 billion tons of biomass, we should have 50 to 60 billion gallons in the 2050 timeframe or so, and that would meet all of the demand for the maritime sector, supply all of the aviation fuel, rail, and a significant portion of the off-road. And so basically it's believed, and the Department of Energy and the other agencies that are working in this space believe that the best use of this biomass is toward these difficult to decarbonize sectors of the transportation economy. So specific challenges in producing sustainable aviation fuel. Airports, unlike gas stations, use a common fueling system. So there are no regional, national, or even international variations, or not significant variations in sustainable in the fuel that's provided at an airport. So when you go to a gas station, you have basically 3 alternatives, and there are differences regionally. The gas that's available in the mountains and Denver is going to be somewhat different than what we see where we live. And it has a lower octane rating, by the way. But that's not the case. If a plane leaves from Memphis, it could go to Knoxville, or it could also go internationally, and it has to have one fuel that works everywhere. Sustainable aviation fuel, therefore, has to be a full drop-in fuel and indistinguishable from jet fuel. So it's identical from a chemical standpoint. Jet fuel is also the lubricant for the engine and the coolant for the engine, and it undergoes extreme temperature swings from being on the ground when it flies at cruising altitude. It's very, very low temperature. So therefore, jet fuel has a complex chemistry and is heavily regulated. So SAF, Sustainable Aviation Fuel, will have to meet the same requirements. So safety is the primary concern. The fuel has to undergo very rigorous testing, very lengthy testing, and testing that is intended to make sure that those who participate and want to supply it have the capital to go the distance. I was on a workshop with the FAA, the Federal Aviation Administration today, and they reiterated that they would like to see SAF come into the marketplace, but safety is first, safety is last, and safety governs everything else in between. And so that's absolutely essential for the future of sustainable aviation fuel. It has to be a drop-in. And so this chart, this is a busy chart, but let me walk through it. This is basically showing the carbon emissions associated with the different subsectors of the aviation sector: general aviation, cargo, passenger, and international. And you can see kind of how it's bumped along over the past few years. You see the COVID dip where we basically just stayed put for a while, and then it's coming roaring back. And so at this point in time, it is likely and it's projected that the aviation sector is going to continue to grow. It's just about caught up with where it was pre-COVID. And if we freeze technology in place, it's going to follow this type of trajectory for carbon emissions by the year 2050. If we go through fleet renewal and we look at that, then it's going to follow this blue curve as old planes are taken out of service and new planes are brought in. We implement new aircraft technology, improvement in operations, and we see that we still do not get where we need to as far as decarbonization. We have much more that we need to do, and so we have to produce a low carbon fuel. 50% emissions reduction SAF is what's shown in green, and then 100% is what's going to be necessary to go ahead and meet the decarbonization goal of 2050. And so the overall takeaway message for this is CO2 reduction strategies in the aviation sector include improved aircraft emissions, include more efficient aircraft, more efficient engines, better operations, but fuel switching and sustainable aviation fuel or decarbonized jet fuel is essential. There's a grand challenge that's out there that was put out by the White House about a year ago. The FAA, the DOE, the EPA, NASA, and others are committed to this, and it calls for 3 billion gallons of SAF by 2030 and full decarbonization, or roughly 35 billion gallons of SAF by 2050. And so if we want to look and see how we're doing, this is another busy chart, but I would direct your attention to the bottom line here. What this is different fuel producers and the amount of SAF that they have announced that they plan to produce in the year that they have made this announcement. And so in the year ending 2022, there's 20 million gallons that's been announced by these entities here in this column. And then you see it growing to the year 2027. And you see that we're a little bit over 1 billion gallons of announced SAF by 2027. There are more that are coming online. There's been significant movements in different legislation that's encouraging more and more of these. And so it looks like industry is very significantly pivoting in this way. Maritime decarbonization. I can take questions or we can launch into this part if you'd like. I only see two, so let's go ahead and continue. Decarbonization of the maritime sector. Basically, the primary challenge of these is just understanding the scope and the difficulty of this particular sector. And so this is a cargo ship. These are used to move goods all across the world. In fact, 80% of the world's goods are shipped on one of these ocean-going vessels. So practically everything that we see in our room and everything that we're dealing with spent some time on one of these vessels. There are roughly 40,000 of these ships that burn between 250 and 300 tons of fuel per day. That amounts to roughly 100 billion gallons per year globally. The US share of that is quite a bit smaller, probably 10 billion gallons or less. But the maritime sector is going to also experience growth over the next few decades. It's not expected to plateau. Shipping and the movement of goods is still paramount to our economy. And we've seen that with the disruptions in the supply chain that we've gone through. Each one of these boxes is essentially an 18-wheeler. And these vessels hold roughly 15,000 to 18,000 of these at any one time. And so these are some pretty unique challenges. It's a pretty unique transportation sector. The distances and the weights that these have to cover basically precludes any kind of serious discussion with electrification. The ships would basically just be hauling batteries back and forth instead of cargo. And so that won't work. And so the International Maritime Organization, the IMO, governs shipping, and they are looking at a proposed mandate of 50% CO2 reduction by 2050. And they estimate that the largest component of these of the decarbonization strategy is still going to have to come from fuel. It's very similar to the aviation sector, as you see in the chart on the right. We can do and implement better design, although these engines themselves are quite efficient the overall design of the ship and the overall design of all the housekeeping loads on the ship would bring about some improvements. There are improved operational measures that can be implemented, but the largest segment and the necessary segment to get to a decarbonization goal is by fuel switching and switching to a decarbonized fuel. So biofuels have an opportunity to make an impact in the near term if they can be used with these ships today. And so these ships, unlike planes, use a very heavy fuel oil. It's called HFO, heavy fuel oil. It's a lower quality and lower cost fuel. It's a residual. It's basically what's left over. The ships contain onboard heating and processing equipment so they can deal with it. There are fewer regulations, although regulations are becoming an important issue. Sulfur was regulated a few years ago, and so now we're seeing carbon regulations come into the forefront. The maritime sector is considering multiple options. Methanol, green methanol, also ammonia is being considered. And so we're looking at the viability of we can use a cheaper form of biofuel if it can serve this maritime sector. And so you see the heavy fuel oil over here on the right. It has the consistency of a thick molasses, and it's not that dissimilar from some of the biofuels that have not been fully processed. And so it's possible that the aviation fuel and marine fuel could come out of the same biorefinery. That's a hypothesis that we're exploring right now. It's a study that we're evaluating as we speak. So trends and needs. Why don't we just go ahead and go all the way to the end and we'll take questions. Trends and needs. Future trends. I see that there's going to be continued research, development, and deployment of these new biofuels. Major industries, big oil, the automobile sector, the aviation sector, the maritime sector are all pivoting in a very serious way toward decarbonization. The snippets on the right are just press releases that I found on the web in just a couple of minutes. There was actually a major announcement yesterday of a new SAF specific facility in Georgia. I'm sure they're looking at the Atlanta airport as one of their customers. And so this is becoming more commonplace, these significant announcements. I think sustainable aviation fuel deployment is likely to continue. It is already in some of the airports in California, and I think it's going to spread throughout the country and across the globe. But the main point that I would offer here is that there's going to need to be multiple viable solutions. This is not a single solution type thing. There's going to be multiple solutions that are going to be necessary that have to be investigated for any of this to work. Competition is going to be keen, not just between different parts of the airline sector or the maritime sector, but between those sectors themselves and other sectors that are wanting to go ahead and access biofuels. Significant needs in this transformation. There's a lot. I've just listed a few here. More awareness among the public. So what we're doing here is a pretty good thing. It helps spread the word a little bit. The public needs to know more about what's going on and why it's important. Better communication of the technical challenges and the opportunities and the changes that are coming about. And so the pros and the cons need to be outlined so that folks understand and can make better and more informed decisions. There's a tremendous number of technical needs. These processing operations are very difficult. Most of them are understood. The science is pretty much worked out. It's to get the costs down and to understand the engineering challenges and the scale-up challenges within. Need to make sure that we have full alignment of the market and the regulatory positions. When those get out of line, it doesn't work. And so we need to make sure that those are in a line. We need, in the ag sector, clearly new crops in production. There's a lot of crops that we know a lot about, but there's more that need to be investigated and looked at. We need to have new techniques, drought tolerant crops, energy crops, so on and so forth. Farmers need to try different things and need to see what works best in the different regions of the country. ground truthing of these carbon reductions. A lot of these are done with models. It's the best science that we can employ at this time, but we need to understand what the real carbon reductions are, and if there are offsets that would take away some of the benefits. We need to understand that, appreciate it, and make changes as needed. Entrepreneurs willing to take risks, and frankly, we need new ideas along the way. And so several acknowledgments, coworkers and friends sponsor the DOE Bioenergy Technologies Office. And with that, I'll close and ready to take questions if there are any.
Great, thank you, Tim. And that's an amazing shot of Oak Ridge there. That's incredible. Looks like Lou has offered a couple questions. Actually, what I'll do here is I'll let Lou jump on our side over here, so he
Sure.
can go ahead and jump in. Lou, do you have a? I'll put you on this side. If you have a mic ready, please go ahead and speak up.
All right. Can you hear me now?
Yeah, we can.
Hey, Tim.
Hi, Lou.
Man, great talk, man. That is so good. Appreciate it. I had a few questions for you.
Yeah.
One is, you said there's a $60 offered price was your reference.
Yeah.
What is that unit?
Per ton, per dry ton
of biomass, and there's no particular grading system to that?
No. Yeah, you got to one of the weaknesses of some of these analyses right at the top. The analyses that we do not factor in a quality part. So with forest residue, you're going to get, nice chips, which I showed. You're also going to get bark, leaves, twigs, so on and so forth. So the processing part, you'll lose some. And then basically, there's not a real good quality consideration. We're doing some work to try to make sure that we can handle and process a wide variety so that we don't have to just throw away the part that doesn't meet the quality standards that the biorefinery needs. But those are not in these analyses yet. And so you hit the nail on the head. That's one of the limitations.
Okay. The other thing I had was you talked about sequestration. Do you mean by that leaving carbon in the soil, or do you mean sequestration as you use the product in a combustion process?
Yeah. That's another good question, Lou. Basically, I think DOE would consider all of the above. What is generally meant is geologic storage. Okay, they find the right kind of geologic conditions and they pump the CO2 underground. It basically solidifies and there it stays. Other options are considered, so enhancing the soil organic carbon across the fields, that counts, and that can and should be considered. Our analyses can consider that. And then the other option that people are looking at quite a bit is just durable materials. And so if we can substitute wood-based product or bio-derived product and it have a long, it lasts a long time. And there, I think the time frame is considered to be 100 years. So if you could put together a bio-based building and that lasts for 100 years, then that's considered to be sufficient that you can count that as sequestered as well. And there's all kinds of other carbon removal technologies that I didn't get into.
Yeah, but for aviation and marine, you're not going to be able to sequester too much. So, right.
No, it would come off the conversion facility and then it would have to be sequestered geologically. I will say, I know there's some interest in actually capturing the CO2 on some of these large ocean-going vessels and then basically chemically binding it and storing it in the ocean as a rock where it would just basically settle on the ocean floor. That's way on out there, but I know that there are folks that are interested in that.
Oh, everything's possible. Everything. All right, one last question for you, and let you move on. But the inevitable question of competing for energy versus food comes up in these topics. What where do your studies say about that?
Yeah. So as you well know, corn production and corn productivity increases every year. And so it has grown and grew substantially in the 2000s, the use of corn ethanol or corn for fuel ethanol. At this point in time, as I understand it, a significant amount of the corn that's crushed is actually split. The starch is used to make corn ethanol, and then the protein is used to make DGG. And so that's used as animal feed. And so the folks that we work with that study this closely are convinced that it's not food versus fuel, but really it's food and fuel, and that the two markets together make sure that farmers have adequate markets to sell their product, because the real problem is when farms decide that they can't make money at all, and so they sell the farm and you put a little strip mall on it, and then that's lost to ag. And so that is what they consider to be the real issue. For everything that we're doing in the future, we're employing limits on the amount of food-based feedstocks that would be used, and that basically everything else would be cellulosic and so on.
Okay, as long as you're not threatening my grain-fed beef, you're okay.
I'm not threatening your grain-fed beef, Lou.
Okay, very good. Excellent, excellent talk. I really do appreciate it. Okay,
well, thank you. Appreciate that.
Yep, we'll stay here for, if there are any other questions, please feel free to put those in the chat. We'll just wait a second or two. That was a really enlightening talk. Are there any more advancements in terms of SAF fuel for, or biofuels for any of the aviation? We can sit there and see all the headlines about Virgin Atlantic buying all these and United investing in different supersonic planes, whatever have you. But are there any hands-on experience? Because you'll hear, oh, hey, so-and-so tried, flying with biofuels, in a, 707 or something like that. Has there been any tangible results from this?
Well, United is pretty serious about it. They have bought sustainable aviation fuel. I'm told that it's available in California, and that if you fly out of San Francisco or LAX, that because it's a single tank, that there's sustainable aviation fuel in that. And so the way it works is United pays for it, so United gets the credit and gets the publicity, but everybody's using it because there's a single tank. Now, obviously, it's quite dilute. On that FAA workshop that I was attending today, the FAA has a significant amount of money that is part of our recent legislation, and they're going to be issuing funding opportunity announcements, or however they describe it, in the near future. Today, most of the SAF, if not all of the SAF that's in production, is using fats, oils, and greases as the primary feedstock through what's called the HEFA process. And then in time, and I think the next one up would be two different options. One of them would be ethanol to jet, is a technology that a lot of people are excited about, because you can start with some of that 15 billion gallons of ethanol that's available today. If and when EVs take a larger share, then there will be demand destruction of that ethanol. And so we don't want to see the farming community suffer as a result. So ethanol to jet makes some sense, and there's companies that are investing in that. And then there's companies that are investing in the little bit more understood technology of gasification, followed by Fischer-Tropsch catalyst that would make a jet fuel.
What have been some of the results? Like, have there been any long-term studies on what the effects of using these types of biofuels or SAF materials have been on not just the environment, but actually on the components themselves and the engine of the planes?
No, that's a really, really good question. The answer is yes. The FAA is a very, very conservative organization, and they don't mind telling people no. Okay. And so these have been studied. They are being studied. And when I mentioned the fact that SAF has complex chemistry, one of the things that they want to make sure that they do is protect the components, including the elastomers, the seals, and everything else. And so the different chemical compositions have different functions. And one of them is to protect seal swelling, to make sure that your seals don't all of a sudden dehydrate and change. And so that's being considered and looked at. I believe that they've done a fair number of durability studies. Well, I'm sure they have. They wouldn't be in production if they hadn't. The amount of hours that's required is significant. I don't remember that off the top of my head, but I do know that it's such that it's set deliberately to allow major players, not labs and upstarts. Okay. And so they have to test significant quantities of fuel for significant numbers of hours. Hundreds, I believe. But don't quote me on the exact number.
No, definitely. Thank you for that. I was always curious about that. I'd always see a headline or something around that, but great to hear that's not an issue.
And right now, SAF is only available as a blend. In some cases, it's a 10% blend. And then in other cases, it's a 50-50 blend with jet fuel. And that is to make sure that there's sufficient jet fuel there to protect and provide the different functions that jet fuel needs to do. So that's kind of what they're looking at right now and how they're introducing it into the market.
All right, very cool. I think if there are no other questions, we'll go ahead and end our session there. Thank you, Tim. And our talk will be posted on our FIT website. Thank you, everyone, for joining. Appreciate it. Thank you, Tim. Thanks again.
All right. Thank you. Appreciate
Thank you,
it.
Tim. See you.
Thank you. Bye.
Take care.
Thanks, Lou.
Yeah, thank you.